Hi everyone. Just addressing your feedback from today. What do you mean when you say the equilibrium that dominates the solution? So what I mean is, okay, there will frequently, not frequently, but there can be multiple reactions that can occur in a solution. And each of those reactions might be governed by an equilibrium process. Those reactions, I mean, every reaction in theory is an equilibrium reaction, meaning they go forward, they go backwards. Some of them go forward more than the other ones. The ones that go forward more are the more important reactions. Their concentrations are more determined by that equilibrium than another one. So let me give you an example. This is another question somebody had. Between these two reactions that I wrote up, and between H2O your question was, which of these reactions produces more hydronium, H3O plus, and how do you know? So in theory, these are both technically equilibrium reactions. They both, every reaction in principle is reversible and an equilibrium and can attain equilibrium. Uh, this reaction is an equilibrium reaction that is heavily skewed towards the products. The equilibrium constant for HCl donating of protons is around 10 to the 6. So I'll say approximately because I don't know the exact value, but it's around a million. This reaction, the equilibrium constant is, well, it's actually equal to 10 to the negative 14. Meaning that if I were going to make these arrows, more representative, I would say this one has a very large forward reaction and only a very, very small backwards arrow. This one has a very small forwards arrow and a very large backwards arrow in terms of, okay, for this reaction is dominant in the sense of the hydronium concentration is most directly determined by this reaction. That reaction goes to completion, and so you get a ton of hydronium being produced. In theory, this reaction also could produce hydronium, but because this one has a very small equilibrium constant, we say that this is not the dominant source of hydronium. It's not going to be the dominant reaction in the equilibrium system. How do you know whether to use concentrations or moles in ICE tables? Generally, you should always be, there's some wiggle room on this, but to be safe, always use concentrations or partial pressures if you're dealing with a gaseous system. Don't use moles. I'll just say blanket statement. Don't use moles. You can use. I use ice tables. To sort of keep track of my stoichiometry. I admit I conceptualize those two a little bit differently. What I was doing there was just, I guess in some sense, whether you call it an ice table or not is kind of unimportant. I was just showing the initial amount, how much it changed by, and how much I end up with. An equilibrium problem, that last step is what you end up with is usually the equilibrium concentration. And when I was just doing it in terms of molality, stoichiometry, limiting reactants, something just going forward, I was doing that in terms of moles. If you're doing anything where you know a reaction goes to completion, and you just want to know how much of this reacts with how much of that, that you should do in moles. If you're doing an equilibrium concentration where you know, okay, I don't know exactly how much reacts with how much of this, but I know that at the end their concentration should be governed by the law of mass action. The law of mass action is written in terms of concentrations. It's expressed in terms of concentrations. And so you should do your icebox calculations for equilibrium reactions in concentrations. If you're doing an icebox for a non-equilibrium problem, like you're just doing stoichiometry, limiting reactants, and just saying, okay, this reacts completely with this and gives me so much of that, that you can do and should do in terms of moles, not molarity. How can you tell immediately between strong and weak acids and bases? There's two ways you can do it. One is that weak acids have small Kas. They have small equilibrium constants. So if I were going to replace this with HF, and I would get this to be F minus, the equilibrium constant for this reaction is about 10 to the negative 4. So weak acids have smaller equilibrium constants than strong acids, significantly so. Strong acids are those that have equilibrium constants, acid dissociation constants that are greater than 10 to the 3. I'm spitballing a number, but very large values, those that go to completion. So how can you know that immediately? You can either look at the K values. That might not be given to you. And in fact, frequently you won't be given K values for strong acids because we usually don't use them. We just assume it goes to completions and we never have to actually apply the law of mass action and calculate concentrations. We just assume it goes all the way to products. The other way to know immediately is another method. It's a different approach. It is more a memorization approach, but I think it's one that is valid and you should do, which is memorize the strong acids and bases. There's only a small handful of strong acids and another small handful of strong bases. The strong acids are going to be HCl, HBr, HI. 3 of the hydrogen halide acids are going to be strong acids. HF is a weak acid. That's the one exception there. Sulfuric acid is a strong acid. Nitric acid is a strong acid. And chloric acid, I believe chloric acid is also considered a strong acid, but I admit I'm a little shaky on that one. But definitely know these 5 strong acids. Everything else which behaves acidically is a weak acid. So it's a small number of strong acids to remember, and then if you see something and you get some indication that it's an acid, you can assume if it's not one of these, then it's definitely a strong acid. Or rather, it's definitely a weak acid. If you're given a Ka, if you're given an equilibrium constant, or an acid dissociation constant for an acid, it's almost certainly a weak acid. These acids, I frequently won't give you a K value because I meaning me when I write the exams, and also when you see problems in textbooks or problems on a standardized test, they won't give you K values for these. You just assume they're strong acids. So you should have those memorized. For the strong bases, the most important strong bases you should know are going to be sodium hydroxide, lithium hydroxide, basically all the metal hydroxides are strong bases. So, or not the metal hydroxide, the alkali metal hydroxides are strong bases. Another strong base, I'm just thinking off the top of my head, strong bases. Sodium hydride is technically a very, very strong base, although it's unusual that you'll see it come up. Those are the strong bases. Anything else you can assume is a weak base if you were told that it's a weak base. Along those lines, How do you tell if a reaction goes to completion? Reactions that go to completion are ones that have very large K values, meaning products are heavily favored. Um, so there's a corollary to that question, which is somebody asked, if K is smaller than 1, can you assume the reaction does not go to completion? Yeah, that's correct. If K is less than 1, meaning it's not large, then that reaction did not go to completion. If K is very large, meaning it is much larger than 1, so I will say anything like, say, greater than 1,000, that's a reaction you can assume goes to completion. How do you tell if a reaction goes to completion? I'll again tell you there's two ways you can either understand it in terms of the equilibrium constants. Larger equilibrium constants go to completion. You might not always be given equilibrium constants, or we expect you to have some basic knowledge about reactions that go to completion. So the reactions that go to completion are any reactions between strong acids and bases, and reactions between, strong acids and bases, and reactions between strong bases and acids. So strong acids, again, are ones that very readily donate protons, either to water or some other base. So I could have a reaction here between HCl and water, or it could be some base. It could be something like the fluoride ion. The fluoride ion is the conjugate base of hydrofluoric acid. So it has a tendency to accept protons, to go backward. So if I mix HCl with a fluoride solution, the hydrogens are almost completely transferred onto the fluoride ion, and what I get is HF being produced almost to completion, and the chloride ion. That reaction would also go to completion. So any reaction where you have a strong acid or a strong base, something that usually has a large K value, those reactions you assume can go to completion. Let me see here. So for example, there was another reaction here I gave. Somebody was asking, so when you had 1 liter of 1 molar HCl and 100 mils of 1 molar sodium hydroxide, did that reaction go to completion? Yes, it did. If I have a reaction like this, HCl this is a reaction between a strong acid, so here it is, it's one of the strong acids, and something else. Or conversely, you could think this is a reaction between a strong base and something else. So I have a strong acid, strong base, those will completely react. So that one also goes to completion. Is the autoionization of water always in the reaction? So this, I'm sorry, this was worded a little peculiarly. Is the autoionization of water always in the reactions that go to completion? Are there any exceptions? I would not say that the autoionization of water is in reactions that go to completion. I think of the autoionization of water as being its own reaction. It's a reaction that occurs in parallel with another reaction, meaning that they're both happening in the same beaker, in the same system. You have a reaction, like if I dissolve HCl in water, this reaction happens to completion, and it happens to completion. But because the reaction is happening in an aqueous solution, there is also the autoionization reaction. Now that might not be an important consideration for whatever problem you're looking at, but it's something to always be aware occurs. Anytime you have an aqueous solution, this reaction between water can occur and does occur. So I would say that there are no exceptions to that. Anytime you're dealing with a water-based solution, the autoionization of water needs to be considered. Whether this reaction went to completion or not, it would still be there. So even if this were a reaction between hydrofluoric acid and water, and it didn't go to completion, this autoionization reaction would still be at play because, again, this reaction between HF and water is happening in water. So this reaction is also present. When the reaction is dominant, but when a reaction is dominant but doesn't produce hydronium, do we then use the autoionization of water? Yes, and I think this question, I'm not certain, but I think this question is in relationship to the last example I did in the 9 a.m. class, where I was showing a weak base acting in water. So for people who didn't see this, I'll re-emphasize this here. If I have a weak base like ammonia in water, ammonia as a weak base will donate, or rather accept, protons from water and produce ammonia, and subsequently leave hydroxide ions. So this reaction is not a strong source, or is not a dominant source of hydronium ions. It is, however, a dominant source of hydroxide ions. If we are curious about, or we want to know what is the hydronium concentration, then we need to consider other possible sources of hydronium ions. And if this ammonia is the only substance in the solution, then the only other source of hydronium ions is from the autoionization of water. So this reaction does not go very far forward. It's only about 10 to the negative 14. This reaction also doesn't go far forward, but it goes further forward than this reaction. It's about 10 to the negative 5. So the dominant reaction, the reaction that has the largest equilibrium constant and sort of sets the pace for everything else, is this reaction. Because it has a large K value, it is going to be the one that determines the concentration of hydroxide ions. Now, to actually do that calculation, to actually figure that out, you'd need to do an icebox calculation. And so you can do that. Once you do that, though, then you can assume this reaction, its equilibrium concentration is set by the other reaction. This one goes far forward and produces a lot of hydroxide ions. This reaction on its own doesn't produce many hydroxide ions, but there will be excess hydroxide ions present because of the other reaction going further forward than this one does. And then once you get that, you can say, okay, these two guys, their concentrations should be related to each other by the autoionization reaction expression. So you can solve for one given the other. Are there going to be any very complex problems on the test? I may have one very complex problem. I recognize that on a test, you have a finite amount of time. I will definitely give complex, complicated problems on the homework, where in theory you have upwards of a week to work on them, and you should take time to work on them. On an exam, I recognize you only have 50 minutes, and there are other things I need to assess. So I may have one complicated problem, which I recognize is going to take people a little bit more time. But that won't be all that there is on the test. Will Ka and Kb be given if we're asked similar questions on a test? Generally speaking, yes. If you need to do a calculation that requires knowledge of an equilibrium constant, I will give you that equilibrium constant. It'd be very unfair of me to expect you to have the actual values of equilibrium constants given. There are some times when I will say you ought to be able to estimate a Ka. Very few examples like that, but in theory, I think it's reasonable to ask you to estimate which has a larger Ka, hydrobromic acid or acetic acid. Well, hydrobromic acid is a strong acid. Acetic acid, I don't know if that's a weak acid, but I know it's not one of the strong acids. So acetic acid is a weak acid. Hydrobromic acid is a strong acid. It completely donates the proton. Acetic acid is a weak acid. It doesn't completely donate the proton. So hydrobromic acid should have a larger K value than acetic acid. But other than that, I will give you the values. Those types of questions are going to be few and far between. Otherwise, I will give you the value, or I'll give you enough information that you can calculate it on your own. Okay, one last point here. Somebody said, I'm still having difficulty determining changes in concentrations in icebox calculations. For that, I would say come see me during office hours, get lots of practice in. I'll do one quick example of how you would do that right now. So let's say I had this reaction, A plus 3B in equilibrium with 2C, and I tell you that your initial concentrations are 1 molar, 2 molar, and 7 molar. And I'll also tell you that the equilibrium constant has the value of 5. And I might want to know, okay, how does this reaction shift? What are the equilibrium concentrations? I'm not going to work through the whole mathematical problem. I'm just going to show you how you would set this up. So, at this point, I don't know whether the reaction is going to shift forward or shift backwards. Almost all the other examples we've seen, it was always like, okay, there was none of this reactant. So this reaction will definitely go shift to the left to produce reactant. Or there was no product, so the reaction definitely shift towards the products to produce more products. Here it's not clear, so to decide we need to calculate the reaction quotient. The reaction quotient should be equal to concentration of C squared, concentration of B cubed, concentration of A to the first power. So I calculate Q should be equal to 7 squared over 2 cubed times 1. That ends up being equal to 6.125. So I can say Q is greater than K, which means the reaction shifts towards the reactants. I have too many products, the reaction will shift towards the products. So I should lose reactants and generate products. So I will generate 1 mole of A, because it's 1 molar. I generate 3 moles of B, and I lose 2 moles of C, or however much. I mean, I don't know exactly how much, but I know that these are the relative ratios. Then I can add all of these columns together, and I get 1 plus X, 2 plus 3X, 7 minus 2X, and these will be my equilibrium concentrations. And those I would plug into the law of mass action and solve for X. So I would have 7 minus 2X squared over 2 plus 3X cubed times 1 plus X. And again, I'm not going to work through how to do that calculation because that is not a trivial algebraic problem to solve. I would do that just on a computer. And I would not give you a question that complicated. But in terms of like the logical flow, how do you solve an equilibrium problem? This is it. And once you get to this point, it's just math. So yeah, hope that was a quick run through about how do you determine changes in concentration. If you have further questions, I would say come see me. We'll work on some example problems and we'll get some practice in. Okay, other than that, I'm going to post a secondary video where I work through the other example calculations I didn't have time to do in lab. I will post that as a separate video for people, and I will see everybody on Wednesday. Have a good, or on Friday. Have a good day.